When we were computing integrals of single variable functions, our goal was to find the area underneath the graph. In the multivariate case, our goal is going to be very similar, except now we're going to be trying to compute the volume under a function of n variables, whatever that means. For the sake of concreteness, let's say that f is a function of two variables and has a domain D. We write the area under the graph of f as this thing right here. And there's a couple of things to note. The first is the use of the double integrals, right, to indicate that we're integrating over two variables, x and y. The second thing to note is this weird dA thing. And what this means is that we're integrating over the area. Now, there's a couple of problems that we face in multiple dimensions that we didn't face in 1D. So for example, in 1D, domains were all pretty much just intervals, right? In multiple dimensions, you can have weirder things happen. So for example, you could have a rectangle show up, or you could have these weird blobby things with holes inside of them. As a general rule, domains can just be a lot weirder. First things first, though, the easiest set to integrate over is rectangles. So that's what we're going to do first. And again, let's just say that we have a function of two variables, x and y. And a rectangle is the collection of all points between, say, a and b, and y goes between c and d. And we can write this in this format here as a nice convenient shorthand. I'm going to draw this out just so you have an idea of why we call it a rectangle. And here's what D is. We're integrating over this set. In this case, the integral can be written as the integral from a to b, and then the integral from c to d of our function. But we integrate with respect to y first, then with respect to x. And of course, we can flip this, and we can do c to d and then a to b, but this time we integrate x first and then y. Now, importantly, this thing here, when I write this down and I say we're integrating f of x, y, dy, I'm saying that we're treating x as a constant. And this is very, analogous to what we were doing when we computed partial derivatives. And I'd say I'd want to compute the partial with respect to y, and we would hold x as a constant. We're doing the same thing, but this time as an integral. And the same story holds for the other integral. Because I'm computing the integral of f of x, y, dx, in this case, I would treat y as a constant. Let's try an example. So let's say that I give you the function x squared y plus y squared x, and we want to compute that on the rectangle where x goes from 1 to 3 and y goes between -1 and 1. Well, according to what we wrote down before, I can just split this up as follows. And because we're integrating with respect to y, we're going to treat x as a constant. So we're just going to pull out a y squared over 2 and a y cubed over 3. And notice here that I've written y equals -1 to 1, and just to remind me what variable I'm actually substituting -1 and 1 in. So let's plug in the 1. So remember, everywhere we see a y, we're going to put a 1. And we'll do the same thing everywhere we see a y, we're going to put a -1. And notice that these two things are the same, so they're just going to cancel out, and we can simplify this to 2/3 x. And that integral is not too hard to do, so we can just grind it out really quickly, and we get 8/3. Could we have done this the other way? Namely, could we have done this by integrating from -1 to 1, and then 1 to 3 of dx dy? And I really want to point out here that the order of the bounds of integration have changed, and so has this dx dy term, right? It was dy dx before, and now we're doing dx dy. And the answer is yes. So you get the exact same answer if you integrate in the other direction, and I would insist that you try it. It all just ends up being polynomials, and it's not too bad. Let's see what happens then if we integrate over non-rectangles. Again, for concreteness, let's let f be our function of two variables, and let's say we're working on a domain D. Let me draw something here for you. Right, there's our weird little blob. Our goal here is to be able to write D in the following way. So we want to be able to say that x goes between a and b, and y goes between two functions f and g. So if I put this onto our figure, here's a and b. Now I'm going to highlight in yellow here the top function, which this should be g, sorry. And the bottom function there in red is f of x. Right? So all the stuff on top is g, all the stuff on the bottom is f, and this is going to replace the c and d, the numbers c and d from the rectangle case. In this case, when we write out what the integral is, we're still going to get the integral from a to b like we had before, but this time, instead of the integral from c to d, our functions are going to take the place of those numbers. So we're going to integrate from f of x to g of x and dy dx. So what we've done here is we've integrated out the y variables, right? So our answer will depend on y, but then we're going to substitute y equals f of x and y equals g of x. And in doing that, we'll only have x's left over. And so it makes sense to do that outer integral as well. Let's do an example this time. Let's take R to be the region bounded by, say, 4x and x squared. And let's find the integral of x squared plus y. I'm going to start by sketching this thing out for you. Okay, so we're integrating over this space. Let's figure out where these two things intersect. In order to do this, of course, I'm going to set 4x to be equal to x squared. We're going to just grind out some algebra here and find that x is 0 and x is 4. So let's label those points onto our graph. We also want to know where the y's go between. So using the fact that y is 4x, we get y is 0 and y is 16. So let's put those down as well. Now let's write this space in that special way that we talked about before. If we look at what x is doing, x is going between 0 and 4. So let's put that in. Now we're going to take a little, right, we're going to choose a kind of candidate x, and we're going to take a walk in the positive y direction, and we're going to take a look at, well, what function do I hit in order to enter R? What function do I hit when I leave R? And those will form the lower bound and upper bound of my new integral. So in this case, it looks like x squared forms the lower bound, 4x forms the upper bound, so that's how we bound y. When I put everything into my integral, I'm going to integrate from 0 to 4, then I'm going to integrate from x squared to 4x, dy dx. So treating y as a constant, we can carry through the integral. And remember, we're going to write this as y equals x squared, so to y equals 4x, so we remember what variables we're plugging in. And if we plug in the 4x into there, we'll pick up a 4x cubed plus 8x squared. We plug in the x squared, we'll pull out an x to the 4 plus x to the 4 over 2. There's a little bit of simplification that we can do here with that latter integral or integrand in particular, so let's do this simplification. And you can compute this. It's this gross number, but this is just a standard integral that we were doing before. I don't want to spend too much time on it. It's not really what we're going for, but compute it yourself and check. Well, once again, we can compute this thing in the other direction, but it requires that we write it down in a slightly different way. So here I've illustrated it, but I've changed a couple of things. So I've written x is y over 4 instead of y equals 4 over x, and I've done the same thing for x. I've written it as the square root of y. And when we look at, well, we want to say, what does y do? Well, y seems to go between 0 and 16. And the next thing we're going to do is we're going to take that horizontal walk along the positive y direction and say, well, the curve that we hit when we enter looks like it's y over 4, and we leave at the square root of y. So those are, again, my upper and lower bounds. So let's plug these into our integral. This is the integral we'd get, but of course this time we're integrating with respect to x first, and you'll get exactly the same answer. I strongly recommend that you try this as an example because you know what the answer should be, so you can try it and go through the motions and get some practice integrating. Finally, we're going to talk about triple integrals, so let's increase the dimension even further. And let's suppose now that we have a function of 3 variables and a domain V. So we're going to compute the 4 volume of this thing, which is a little bit hard to think about, but the 4 volume is the graph under f, and the way that we write this is like this. All right, dv here means that we're integrating with respect to volume again. And again, notice this time we have 3 integrals to integrate that we're integrating in 3 dimensions. Let me draw what something might look like in 3 dimensions. All right, so this is the space that we want to integrate over. And let's say that we can bound v above by the function psi of x and below by the function phi of x, where x takes in the values in this domain D. Okay, so we can write that as xy being in D, and then z being bounded between phi and psi. So when I write down now the triple integral, I'm going to be able to write it in the following form. So the integral over d, and then I'm going to integrate z from phi to psi. And here, again, notice that I've integrated away the z's, so the only thing that's left over are x's and y's, and this integral makes sense. Now, our goal here is to bootstrap this down and say, well, hopefully I can do to the domain D, where x and y live, the same thing that we did when we were computing the double integral. So we can write it as x between a and b and y between f and g, just like this. And then I'll be able to expand out that integral that I had above. Let me just rewrite down the whole thing. That double integral over d will become the integral from a to b and the integral from f to g. Right? And so we get this big ugly thing. Now in practice, again, we're not going to bootstrap it by saying, well, let's look at the domain D. We're just going to kind of take our entire set V and write it directly by saying, okay, x goes between a and b, y goes between f of x and g of x, and z goes between phi and psi. So we kind of end up doing all of that at once rather than this iterative process. And you'll see it in a second as we do the next example. Okay, so let's do a triple integral. Let's say that V is the region in the first octant, and the first octant is just the place where all of the coordinates are non-negative. And let's say that V is the region bounded by 4 minus x squared, y equals x, z equals 0, and y equals 0. And let's integrate just the function y. Well, we've got to figure out what this thing looks like, so let's draw a couple of them. I think z equals 0 is probably the easiest one to draw. That's just the xy plane. The exact same sort of reasoning is going to hold for y equals 0. That's the xz plane. Things start to get a little bit more complicated for the other two. Let's do z is equal to 4 minus x squared. And let's start by actually drawing z equals 4 minus x squared in the xz plane. Now, y doesn't matter, right? There's no y's in this. So what just ends up happening is we get this constant shell kind of coming out in the y direction, like this. Okay, which is a little bit nasty. And if we do y equals x, same sort of story. We're going to draw the curve y equals x in the xy plane. And of course, z doesn't matter, so we're able to just, kind of stretch that line out in the z direction. Now we've got to put all of these together, and it's not too bad, but it's not trivial either. You're going to have to think about what happens if you kind of intersect all four of these things. And when we get something that looks like this, all right, kind of a weird cheese wedge. Let's figure out some of these points. So z is equal to 4 minus x squared. So this top point up here has a z coordinate of 4, and the other coordinates are 0. In the bottom left-hand corner, that corresponds to when z is 0. So if we solve that for x, we know that its x coordinate is 2, and all the others are 0. And finally, we have this coordinate, and it lies on the curve y equals x. So we know that the y and the x numbers are going to be the same, and z is equal to 0 because it's actually in the xy plane. All right, if we actually now try and figure out how to write down v, we're going to say, well, it looks like x goes between 0 and 2. That's no problem. But to figure out what y goes between, let's draw this little triangle, and hopefully you can see where this triangle comes from. It's sitting in the xy plane there. If we choose kind of a typical candidate x and take a little walk in the positive y direction, we can see that we're going to enter when y is equal to 0, and we're going to leave when y equals x. So those are our bounds there. For the last coordinate, we're going to choose kind of a representative point with coordinates x and y, and we're going to take a walk in the positive z direction. And as we do that, we're going to enter our space when z is equal to 0, and we're going to leave our space when z is equal to 4 minus x squared. So those are our bounds. And generally, these do depend on x and y, but in this very special case, they only seem to depend, well, one of them is constant, the other one is just x. Having written our space, we are now in a position that we can actually set up the integral. So the integral is going to go from 0 to 2, then from 0 to x, then from 0 to 4 minus x squared. And we're integrating that as dz, dy, dx. And we can carry through this integral just as a little bit of practice, remembering that z is a constant, so we just get y times z. Certainly when I plug in z equals 0, nothing is going to happen. So I'm just going to plug in, z is 4 minus x squared, and we get this. We're integrating with respect to y, so we're going to pick out a y squared over 2 term. And when I plug in y equals 0, nothing happens. So again, what happens when y equals x? Well, we get this guy here. This is, again, just a polynomial, so we're fairly good at integrating these, and we work through all of the math, and we get 32/15. You are free to try to do this one in different directions. Maybe you want to start instead, of integrating dz, dy, dx, you want to do dx, dz, dy, or something like that. There's lots of different combinations with this one that you can practice, but they'll all give you the same answer. And this takes care of iterated integrals. I think, one thing that you are going to want to, keep a lookout for is that as you try, when you integrate over non-rectangles, if you integrate in the x direction, then the y direction, it's, even though your final number at the end will be the same, the intermediate steps in order to get there are very, very different. And so there are some integrals that are actually impossible to integrate if you do them in a certain order. So maybe xy doesn't work, but if you switch them, yx does. So it's important that you, when you're doing examples, try doing both directions. It's great practice, but more importantly, if you get stuck in one direction, it might turn out that the other direction works in a better way.